Hello students, and welcome to another algebra lesson from Mr. Graves. Good to see each of you through the camera. Hopefully you are having a good day. Our last section on factoring, and I want to go over it today and talk to you about factoring completely. Just a few last examples to try to help you out, and hopefully this will be a help for you. Greatest common factor continues to be a theme. So let's start with it in our first example here. We have 5ax to the fifth minus 5axy to the fourth. We always have to factor out everything that we can in a problem. So doing that, it looks like there's a 5 that's common. There's also an a that is common and an x that is also common. But we can only pull out one x. All right? There's 5 here and 1 here. Y's are not common. We only have it in the second term. So 5ax is our greatest common factor. We'll put the minus there. So 5ax times what gives us x to the fifth? Well, the answer there would be x to the fourth. And then 5ax times what gives us y, or gives us the second term? That would be y to the fourth. Okay? Now, we notice here that we've got some perfect squares going on. And in doing that, we're going to write down 5ax times, and look at what we get here. We have a minus, a what times a what here, and a what times a what here. So, what times what is x to the fourth? Well, that would be x squared minus y squared. X squared plus y squared. So you notice that we have a set there, breaks down into here. Well, we have one more step, don't we? Because this particular binomial is also a perfect square. It has a minus, and it also has a first and a second term that basically are perfect squares. What times what is x squared? X. What times what is y squared? Y. So let's write 5ax, and let's write what the perfect square set of binomials is for just this. Well, that would be x plus y and x minus y. And then this here in particular, we just bring it down. It has a minus, so it can't be expanded anymore. So there we go. All right. This turned out to here, and it worked out obviously in such a way that we had sets of perfect squares that we continued to bring down. All right. Now, another unique situation here. We have an x to the fourth minus 9x squared plus 8. And those of you that are my students, you can be looking, of course, in curriculum. There are no common monomials. There's no special patterns to a trinomial like that. But we do factor by finding the factors, and I wrote it down for you, the factors of a positive 8 whose sum turns out to be a negative 9. Well, the answer to that would be a minus 1 and a minus 8. Okay, so those multiplied together give us our positive 8, but when added together give us our negative 9, all right? And x to the fourth perfect square is going to be x squared and x squared, all right? So we got an x squared minus 1 and an x squared minus 8, and it looks as though we've also got a perfect square. And in your book, if you follow, and this one's a little bit unique, we factor that first binomial because it is different squares. So x squared minus 1. What times what is x squared? X. What times what is 1? 1. X minus 1, x plus 1, and then we bring down the x squared minus 8. 8 is not a perfect square, so that second part can't be split up. All right? So that kind of gives you that. Now, these last three problems are a little bit unique. All we do is actually group them in two sets of binomials, and let's see what happens, all right? 2xy minus 7x. We're going to put that kind of in parentheses, and then we're going to put the second in parentheses, plus 10y minus 35, all right? And we realize here, and I'll just flip my book here, we end up in a situation where because we've got two binomials, now we look at them, or two sets of them, we look at them and we see what is it can we pull out. So we look at the first, 2 and 7 we can't, but notice there's an x in each one. And if we pull out that x, then we're going to get this. X times what gives us 2xy? Well, that would be 2y. X times what gives us a 7x? That would be 7, all right? Plus, we have a 10 and a 35. And if we were to break those down, 10 is 2 times 5, 35 is 7 times 5, so we actually have 5 as a common factor. So y cannot be factored, but we do have a 5. So we'll put a 5 there in our parentheses. And you guessed it, it's probably going to come out just like this. We did this on a lesson the other day. So 5 times what is 10y? 2y. 5 times what is 35? 7. And look here, we have 2y minus 7. And just remember, in review, let's see here, let's do 7x plus 4x equals 11x. 7 and 4, we can add those because why? We have a common term, combining like terms. Well, the same is true for binomials. We can add x plus 5 because there's a common term, and 2y minus 7 and 2y minus 7 act like our x's even though they're binomials. So we get x plus 5 times 2y minus 7, and that's our answer. When you break down these polynomials into two binomials and factor, the problem usually ends up being perfect in that what's in parentheses is the same, or else it wouldn't work. All right, let's try it here. am minus an, we're going to put parentheses around the first two. Remember, it's an automatic plus. Even though there's a minus there, we're going to put that minus inside the parentheses, and there we go. All right. Now, we're going to take a look here, and in doing am minus an, we know that we have a common, greatest common factor is a, so a times a, or m minus n, all right? And then in this particular case here, and I'll just make sure I have my handy-dandy book so I don't get the sign wrong, all right? It looks as though plus the negative, all right? So we'll pull that plus, and then a negative, negative p, all right? Let me take a look here. Negative p, and then, whoops, plus a negative p minus p times, and then we'll get in parentheses here. P's are our greatest common factor. P times what is the Pn? That's m. And then P times Pn, or times what is Pn? We get the n there as well. All right. So it looks as though the I'm sorry, that's a minus there. There has to be a minus. These minus times minus is a plus. All right. So a minus p times the m minus n that we have ends up giving us our answer. All right. Then, on the last one, we're going to divide our binomials into two. So it's kind of like right in here again, all right? So 2y to the third plus 5y squared, all right? Automatic plus negative 8y minus 20, okay? And again, we've got greatest common factor, and we can pull these apart, and it'll kind of show you what we're doing here. So what can we pull out? The numbers we can't pull out, the 2 and the y, that won't work. All right, but we can pull two y's out. So let's do y squared. All right, so y squared times what gives us 2y to the third? 2y. We're going to pick up 1y. All right, plus 5, and there's no letters there because y squared and y squared. All right, and then we end up having the negative 8 minus 20. Get my sign right again. All right, and it looks like we can pull out the 4. So we've got a minus 4. All right, and then we pull out 8 would be 2 times 2 times 2, we get that. So 4 times what is negative 8y? That would be a 2y, all right? 4 times what with a negative 20? That would be a positive 5. So negative times a positive, in this particular case, is the negative that we need, all right? So it looks as though with the 2y's plus 5 is the same binomial, and again, combining like terms and using those as the like terms, we have y squared minus 4 is equal to 2y, or I'm sorry, times 2y plus 5, okay? Remember that your parentheses have to be around each binomial. You can't have the first set not have parentheses. That means a totally different thing. So just remember that, all right? And again, these are just other ways you can factor, especially when you're seeing longer polynomials, most likely in your work or homework. Those are going to be paired off together, and you need to keep the signs right as well. All right, thank you, and have a great day. Take care.